Perfect. All right, Pekan, you do need to unmute. There you go.
Hi, Archana. Thank you. Thanks, Zach, for giving the opportunity to speak at the OCP forum. My today's topic is extending E1.S on the memory accelerators. As we all know that E1.S is a EDSFF form factor, which was predominantly designed for storage class memories, but our aim is to use them for memory accelerators and memory expansion. So let me start the discussion. The biggest challenge in the modern day workloads is how to scale up the memory. The memory capacity has not really scaled up as compared to the CPUs. There are a number of challenges when you increase the memory on a given server. The first one is the real estate. We really do not have any room to add more DIMM slots across the CPU sockets. If you see the picture over here, the designers are trying hard to fit in more DDR slots, but the capacity is already saturated. Another challenge is the high-speed interfaces. All the DDR4, DDR5 parallel interfaces, they add too much of complexity in the PCB design processes. And they need some high technology fabrication methods, which increases the cost. The third and the biggest challenge is the number of pins. As you all know that the DDR4, DDR5 are the parallel interfaces. They use a lot of pins. And it becomes very hard for CPU manufacturers to add dedicated pins just for memory. So adding more DIMM slots on a server is really not a viable option. And therefore, the industry trend is today moving to serial interfaces. So we'll be covering some serial interfaces in the sections next to the slide. Over here, if you see, this slide compares a parallel interface on the left, which is the DDR4 DIMM interface, along with the E1.S EDSFF serial interface. There are two types, or I would say two different configurations of E1.S. An E1.S with 1C connector, which is similar to a PCI Gen 4 Cross 4 interface, and E1.S with a 2C connector, which is similar to 8-lane PCI interface. If you look at the number of pins, the DDR4 takes a standard UDIMM 288 pin connector, has 64 data and 87 sideband pins. But if you look at the E1.S on a similar footprint, the E1.S takes almost only just the 20% of total pins. And if you just compare the data pins, it is only 75% of the number of pins as used in a parallel interface like DDR4. Even if you compare the area of these connectors, you would see that the connector of E1.S takes almost just the 25% of total area of what an equivalent DDR interface connector would take. So you save both on number of pins and the connector area on the PCB. And this actually brings down a lot of complexity on the PCB designs, because you can shrink the design, you can use the room for any other interfaces, and serial interfaces can be routed over long distances on the PCB. So that helps the PCB designers to manufacture low-cost PCBs and scale in the market. While we are here discussing about the EDSFF form factor, there are some added advantages. The EDSFF form factors allow hot plugging. They have interfaces and signals for going into a low power mode. So this greatly enhances system integrators or data center administrators' work, because they can add the modules as they require. You do not have to over provision your system to take care of what comes in future. You can add the memory when it is needed. So it saves your cost. So while the serial memory interfaces are looking good from a data centers or a system integrators point of view, but the question always comes to our mind is whether these serial interfaces can meet the performance and the latency of an equivalent parallel interface like DDR4 or DDR5. So let's look at the performance comparisons. If you look at the performance numbers over here, there is a table on the left-hand side, which compares the PCI performance, and on the right-hand side, there is a DDR4 peak performance numbers. Now, before I go into the details, please look at the units. The DDR4 performance numbers are in megabytes per second. So you have to divide it by a factor of 1024 or 1000 in order to make it comparable to left-hand side figures, which are in gigabytes per second. If you look at the red boxes over here, what you will find is the PCI Gen 4 cross 8 or cross 4 cross 8 interface, which is E1.S, can actually meet DDR4 performance similar to a 2400 or a 2133 data rate. So PCI Gen 4 is still not there to meet up the performance for DDR4. But if you look at the PCI Gen 4 in a E3.S form factor, which is the blue boxes over here, the blue box in the cross 16 column, you will look at that it can meet the entire DDR4 performance up till 3200 data rates. So what we are looking at is, at performance numbers, there is a match between the serial interfaces and the parallel interfaces. And if we go and scale up beyond to PCI Gen 5 data rates on a serial interface, it can actually exceed. The PCI Gen 5 version will have data rates somewhere around 31 gigabytes per second, or even higher, 63 gigabytes per second, which is far more than what DDR4 itself can support. So the summary is that performance is better or equivalent or better in case of serial interfaces. Now, performance is one part. What about the latency? So let's look at the option of reducing the latency on the serial interfaces. We have a lot of options here. There are new protocols in the market which are like cache coherent interfaces, interconnects, and C6, CXL, OpenCAPI are few of them. These interfaces are designed to reduce the latency on the serial side of the bus. They have their own packet structure, which is optimized for memory load and store performances. So what you get is a high performance from a serial interface and a low latency from a cache coherent interconnect. Combining the two in an EDSFF form factor makes it a very good solution for a memory expansion device. So this is our goal here, to have a EDSFF memory module which can be used as a memory expansion device and augment a DDR bus interface, which is currently saturated. At Smart Modeler, we are working on designing such modules. And one of our prototypes contains or is being built as we speak today. The memory on this prototype is a 64 GB DDR4 memory. It runs a C6 controller, cache coherent controller, which uses the Xilinx FPGA. This Xilinx FPGA also contains a dual cores A72 ARM processor. So it has enough horsepower to run your basic load and do some kind of acceleration. The power profile on this board or this module is somewhere around 25 watts, which is within the E1.S spec. So this is a prototype, as you can see in the picture over here, which can be plugged in the plug to the backplane of a U1 or U2 server and increase the capacity of your memory in a server. Let's talk about the specification. Most of these specifications over here are derived from public standards or the open standards. The E1.S standard, which talks about the mechanical and the electrical details of SFF standard E1.S or E3.S form factors, are available on SNIA website. The FPGA controller, which goes inside this prototype, has all its data sheets available in the public domain. So you do not have to depend on Smart Modeler to design such devices. You can actually build your own. If you look closely, we were talking about the memory expansion case. Now, this is a very interesting use case for some of the system integrators, OEMs, or even the end customers like hyperscalers, because they do not have to over provision their system for future needs. They can add memory whenever they want without shutting the system or without shutting your server or without even opening the chassis. And they would get similar performance and similar latency numbers as what they are seeing currently in DDR4 or will be seeing in DDR5 based parallel interfaces. So we have achieved all the basic requirements which are needed for a memory expansion use case. Now, let me talk a little bit further. It's more of a futuristic view. If you use, since this memory device, which I just showcased, uses an FPGA inside it, you can add more details, more custom functions to it and make it like an accelerator. You can offload your CPU host and add some encryption or compression, which can be run inline along with the memory. Xilinx provides all these tools and reference designs, libraries, which you can use to build these custom hardwares and write software on top of it. There are plenty of material, which I have listed over here, along with the tutorials and trainings, which you can use. And my call to action would be, this is one of the devices which can fit on any given server, which is available from OCP forum, which is like Yosemite V3, or any other CPU host which supports ARM or AMD processors. If you need to need more information about this device, you can always contact at Smart Modeler at the links given below. That's all. Thank you, Krishna.
Yep. Hey, thanks, Pecan. We have about 2 minutes left for questions. And the only comment that I see is on the chat is that they wanted to know if this is still in the planning stage or if it's something that someone can acquire today. Can you talk a little bit about availability of the product?
Yes. So we are designing the product. The product is right now in the advanced stages of layout. And after that, we'll go into the manufacturing. So the first samples would be available somewhere around first quarter of 2021. So that's what we are building our first prototype of these devices, and they can be ordered through Smart Modeler. We'll also make the specification available to the OCP forum once the product is out. Okay, so if there are no further questions.
Yeah, that was the only question that I saw here. I'm sure if there's more questions, just check back on this session. And if, through the FN virtual site, and then you should be able to see what discussions there are around this topic.
Absolutely.
Okay.
Thank you. Thanks a lot.
Thank you so much. Let's see. Our next speaker is Jessica Gulbrand from Intel. And Jessica, you can share your screen.